Okay. Wait. Started recording, right? Okay. So, good afternoon, everyone. I hope my mic is working. I'm talking right now, so I hope you can hear me. And before we start, let me mention a couple of things. Okay, okay, good. Okay, so at least I'm not talking to myself. Before I start, let me mention a couple of things. For those of you who, in case you still don't know yet, right? The tutorial questions is for you to do by yourself, and during, like, for example, later today, I will show you to do certain questions. So this is for your own exercise. That means do not need to submit to me. What you do need to submit to me is 3 quizzes. So if you look at our course information, okay, we have 3 quizzes over the semester. So this week is actually a trial quiz just to get you used to the system, and then the first real quiz will be on week 6. So I think I can plan to put the quiz on week 6, let's say on Thursday to Friday. So hopefully everyone is okay. So the quiz is normally 24 hours, and I will upload questions on the Moodle page, and it's over here. So I prepared this already. So when the time for the quiz starts, you can go to this page, and then you can submit. You can download the quiz questions from here. Okay, so you can download the quiz questions from here, and then when before the due date, you submit your answers onto this part here. So for students, right, there's a button for you to submit, and then just write your answer, and in whatever you it doesn't matter how you write your answer, as long as it is PDF format, so that you can upload to the Moodle. Okay, any question? Okay, so if you have any question, so 22, yes, tomorrow. So the trial quiz I will have tomorrow. No marks, because you will see the questions are very stupid. So it has no marks, just for you to practice the system only. Okay, so just for you to practice the system. Otherwise, it is no marks. So even if you're already familiar on the PDF kind of things, if you don't want to submit, it's fine. But at least try, right? Just to get used to the thing, because when the real quiz starts, you have 24 hours. So so you don't want to get, panic and things like that. Tests. Do you mean the midterm exam? So our midterm exam, we plan to do it on the week 8. Okay, so it's it's over here, and most probably it will be the Wednesday lecture time. So if you're talking about the test, is here. So you got quiz, the test, and then 2 more quizzes, and then final exam. Okay. So the things that you need to worry about your marks is the quiz and the so all these things. Okay, so all these things. Okay, any other question about quiz or test? Zuri, did I answer your question? Is that what you're asking? Okay, I'm still recording. Everything looks okay. So if you're still not sure, you can ask me some more. Meanwhile, I can continue the story of friction. So we were talking about static friction, right? Any more questions? Looks like everyone okay. I assume everyone here is okay. Let's continue with static friction. Okay. So static friction, right? We stop until this example, 2.2.3 of the lecture notes. So I should try to show this in the recording as well. In the lecture notes, we want to consider a box of mass 1 kg sitting on a rough surface with a coefficient of static friction given to you. Okay, so it's attached to a spring constant of 30, extended by this much, and what is the maximum extension before it's able to slip over the surface. So what is happening here is that is this. Okay, so right now this is a rough surface. Okay, so this is a rough surface, and then because there is a rough surface, there's friction. Even if I pull this out, okay, if this moves, the spring will pull it back. But now it is a rough surface, so there is a friction to keep it fixed in this extended position. So what we want to do now is to try to calculate what is the maximum distance you can extend such that this box is still fixed to the surface in this extended position. So we want to draw the free body diagram and try to solve the system. Let me get my red pen. Okay, so yeah, so to solve this, we just need to write down the free body diagram for this system. So it is attached to a spring, so the spring will try to pull it back. The magnitude of the force is kx, so the x is whatever number in meters or the extension. And then the reason why it can still remains there is because the net force on it is 0, so we expect there's going to be a static friction. So this system is in equilibrium. If we don't want this to move, that means the net force acting on this is 0. Am I right? So that means the net force, if I take right as positive, so Fs minus Kx, we want this to be 0. And as we can see, as always, it doesn't matter what the x is, the F will automatically be the same value, so that it will cancel out the force to remain in equilibrium. But it can only do so until a maximum point. So where if x is small, the friction is correspondingly small. If x is larger and larger, the friction is larger and larger until there's a maximum value. So when x reaches some maximum value, Fs will be mu s times n, right? So Fs is mu s times n, and I want to know what is this mu s times n. So mu s times n is equals to kx maximum. Sorry, the question is asking for what is the x maximum, right? So to determine the x maximum, we just need to figure out what is n, and n is just the vertical components of the force. So it's sitting on the surface, so we got a normal force, and this spring has a weight. So for the vertical forces, n is equals to mg, so we can substitute this into my n over here, and therefore I got mu s mg is equals to kx maximum. Therefore my x maximum is equals to mu s mg divided by the spring constant. Okay, so yeah, so we just need to plug in the values, right? So the coefficient is given to be 0.400, the box is 1 kg, gravity is 9.8, and spring constant is 30. So if we punch in all the numbers, you get 0.131 meters. Okay, so the maximum distance you can pull this is 0.131. Okay, anything less within 0.131, it will stay there. But if I pull it more than 0.131, the spring force will be quite high. It will overcome, and therefore it will not be remaining in static friction anymore. So my maximum extension is 0.131. Okay. There's a typo in the unit of string constant. Let's see. Oh yeah, Newton per meter. You're right. Kaheng, yeah, thanks. So the spring constant is Newton per meter, right? So K is 30 Newton per meter. So yeah, thanks. So I will fix this. Okay. Anything else? Everyone okay? Okay, so is this too bright? Okay, I think it's better now. Okay, so that's for the that was the final example involving static friction. Now we want to go to kinetic friction. Okay, so kinetic friction is the opposite of static. That means there is relative motion. Okay, so static friction, the main defining property is that for static friction, everything stick to the surface, so there's no relative motion. Okay, so right now, kinetic friction is the situation where there is a relative motion. That means your friction, your object is sliding over the surface, scraping the surface, or slipping the surface. Okay, so sometimes you see these type of words. So that means there is kinetic friction. So this is what we're talking about here is now kinetic friction. The second type of friction that we want to study here. Okay, so this is the friction where there is relative motion. So this friction is much easier than static friction. Okay, so it's just one value, and let me finish writing first. Okay, so relative motion between the object and surface. Okay, so this friction is much simpler because the magnitude is easy and the direction is easy. Okay, so static friction very complicated, right? It is whatever that keep it fixed into place. But for kinetic is just magnitude is very simple. It's just the coefficient times the normal force. You just need to figure out what is the normal force. Okay, so this mu k is called the coefficient of kinetic friction. Okay, and then once you got the magnitude, the direction is opposite the direction of motion. Okay, and of course we are talking about the important point is the relative motion with the surface. Okay, because we only care about with the surface, because if it's touching a surface, kinetic friction, that is what we want to calculate. We don't want to calculate like relative to other things like the earth or the ground and that kind of things. Okay, so yeah, so for hang on, let me switch this back. For kinetic friction is very simple. So let's see how simple it is by just working out a simple example. Okay, so we have a block that is projected forward on a surface. Coefficient of kinetic friction is given, and then initial velocity is given. So how long does it take for it to slow down until it stops? Okay, so this is the defining, this is what happens with kinetic friction. Kinetic friction is a force that will slow down the object. So normally we have been assuming smooth surfaces, so if it's smooth surfaces, then there's no force, then the object can move at constant velocity forever. But this doesn't happen in real life, right? Because real life, if you touch something, there's going to be friction one way or another. And now we can actually calculate precisely how it slows down. Okay, so this is example 2.2.4. I have a rough surface. Okay, so I have a rough surface and then a box that is thrown forward initially at 5 meters per second. Okay, the mass is 1 kg. Okay, so let's put this as m first. The mass is 1 kg and I want to find out the time it takes to slow down. So to slow down, that means I want to calculate the time. So how do we get the time? We can use our knowledge from chapter 1, kinematics, right? So kinematics, if I know the acceleration, I can use the kinematic equation to find the time taken. So that means I need the acceleration. So to get acceleration, I need to use Newton's law, right? So I'm chapter 2 using chapter 1 and 2 to solve this problem. So what are the forces acting on this? So the object is moving forward relative to this surface, therefore the direction of friction will be opposing. This is my kinetic friction. Okay, this object is touching the surface, so there's a normal force, and of course there is a weight, right? So if you're talking about vertical forces, this is in equilibrium in the vertical direction, Therefore, the normal force is equals to the weight. So this one is easy, right? I hope. Okay. And now we talk about horizontal. In the motion along the horizontal direction. So along the horizontal direction, it is not in equilibrium. So what is the net force? There's only one horizontal force acting on this box. It is just Fk, and it is to the left. So let me take right to be positive. Okay, so I got Fk is equals to the net force, right? So this is the net force. And by Newton's law, F equals to ma. Okay, so Fk is the magnitude of kinetic friction is always one number. Okay, it's not like static. Static is like could be 0, could be a maximum, could be anywhere. Over here is just one number, mu k times n, and then this is equals to ma. So I do this extra step to emphasize sometimes you must be careful. The normal force may not always be equals to mg, but for this case, yes. Then you can substitute this inside. I got this one. These two cancel each other. So my acceleration is equals to mu k times g. Okay, so I found the acceleration of the system. It is a constant. So it is just a constant times another constant, right? So now, since my acceleration is a constant, I can use the constant acceleration kinematic equation. So the constant A kinematic equation. Okay, so the constant A kinematic equation, I want to find out how long does it take to slow to a stop, right? So just think of which equation will give you involving time, and you are given the initial speed and then the acceleration. Okay, we don't know the displacement, so better avoid thinking of any equation involving displacement. So we just use this one. So it's v0 plus at. Okay, so my final velocity, I want to find out when it stops. My initial one is just 5. Okay, and then my A is just minus mu k g, and then t. So this t is just u over mu k g. So it is just 5 divided by the coefficient is 0.5, right? And then 9.80. Therefore, if I punch out the numbers, I get 1.02 seconds. So if I round up to two significant figures, it's just around 1 second. If the velocity is not constant, yes, it will still be constant for these kinds of problems. Okay, Wei Zheng? Yeah, so we will, yes, we will, for kinetic friction, we assume it is a constant. But actually, later in the next part, we will learn about a force that is velocity dependent. So this one is velocity independent. Okay, good. Okay, so clear so far, everyone else? Okay, so yeah, so the next example is correct air friction. Yes, that's the next thing we will discuss. Yeah, and that one is a bit more fun, at least not so at least to me. Well, fun as in more things to do lah. Explain this part lah. Okay, so this we are talking about this, right? Okay, basically actually it's nothing. I just write too many. I think I wrote too many things. Basically, I want to find for the horizontal direction, right? What is the net force? Okay, so what is the net force? And then by Newton's law, it's just supposed to be ma. Okay, so for the horizontal force, we just need to do this, and then you look at the free body diagram. Who is the horizontal net force? So there's only one horizontal force here. So therefore, Fk is equal to ma. That's all, right? So I just wrote too many extra things. So shouldn't so it shouldn't be that confusing. It's just something simple. Okay. So that's all we were doing. Okay. So the next problem is this one. So let me. Yeah, I keep doing this because only this part will be recorded in the video, so I need to remember to show this on the screen. The next example is 2.5. Right now I have a sloped surface at the angle alpha. Coefficient of friction is just some number mu, right? So this one is for arbitrary numbers. We just want to find a formula such that the maximum angle just let me read this. What is the maximum angle such that the block remains static on the surface? Okay, so this is a static friction question. I want to find the maximum angle. Okay, so let's try to do this. Okay, so come down. So this is a static friction question. Kinetic friction, not many examples because it's too simple already, right? It's only complicated when we mix it with other situations. So as a pure example, not much to do with that. So right now, what we have here is a box on a slope surface. So the slope is alpha, and I have a static friction. So let's try to draw all the forces acting on this object. Free body diagram, I got the weight. It is sitting on the surface, so I got N over here. And then we want to consider the situation it doesn't move. So if it wants to fall down, right? So the reason why it doesn't move is because there exists a static friction. Okay, what is the direction that you should draw? So just remember, the static friction, it just means that whatever direction to keep it fixed. So it wants to fall down because the gravity will pull it down. So we expect the direction of our friction to be over here. Okay, so you can, it's either this way or this way, right? So even if you guess wrong, normally it's still fine, because even if you guess wrong, right, you will get the answer there's a negative number. So then you know you guessed wrong. You will see more clearly when you solve questions now. Okay, so but for now I think everything should be pretty straightforward. So let's try to resolve the forces. So let me choose this as my directions. Okay, so see, I keep on choosing different directions. It's up to you, as long as it's consistent. So on this side, I got mg cos alpha. The mg resolved to here is mg sine alpha, and the other two are already along these two directions. So let's try to figure out the forces. Let's look at perpendicular to the surface. So on the y direction to surface. So in the forces perpendicular to the surface, this is in equilibrium. So since this is in equilibrium, my normal force will cancel out with the mg cos alpha. So I got the equation for normal force now. And then parallel to the surface. So we are still calculating the equilibrium assumption. So it doesn't move. That means my normal force, my friction will cancel with this force. So mg sine alpha minus static friction is equilibrium. So should be totally add up to 0. Therefore, my friction is mg sine alpha. Okay, so the magnitude, just I was mentioning last time, will be whatever to make sure these two are equal. Okay, so if alpha is 0, then static friction can be 0. If alpha increase a little bit, static friction will be exactly this value until a maximum. So when alpha goes to some maximum value, okay, then static friction will go to its maximum value, and any higher than that, it will start to slide already. So just plug this in, right? So I got mu Sn is equals to mg sine alpha, and then there's an n over here, but I already got the n just now, so just put this whole thing inside, right? So I got mu s mg cos alpha, and then this is mg sine alpha. So I cancel the m. This is alpha max, this is alpha max, right? So I just divide this down. I got the g also will cancel. So if I divide this down, I got tangent alpha, right? So tangent alpha is this. So therefore, my maximum angle is just the inverse tangent of mu. Okay. Okay. So clear so far? So this is the situation I was showing to you last week, right? So I have something on a surface. Okay, so there is some friction, even though the paper is still actually more or less smooth, but not exact super smooth, right? There's some friction. So if I tilt this a little bit, it will remain on the surface, right? So alpha can increase. The static friction will automatically be equal to this magnitude, so that it will remain on the surface. Okay, even if I change alpha, oh, too much, right? So change a bit, it doesn't move, right? The static friction automatically cancel out the net force, right? Automatically, until it goes beyond the maximum. So if I increase my angle too much, it start to fall down already, right? So that's what happens when the words I like to say is I broken the static friction, right? So it's no longer static friction, it starts to move already. Yeah, mu s. So the question didn't put the s there, but if we understood, then it's fine. So it's forgot to write the s, and should put the s there also lah. But sometimes if it's clear, we are only talking about one friction. Sometimes if it's clear we are only talking about one type of friction, then the question don't bother to just label the s. It's already you understood which mu it is. Okay. Anyone else have question? Okay. So if there's no more question, then this was page 2. Okay. The next one is page 3. Okay, so the air resistance kind of thing. Okay, so this is 2.2.3. We are talking about resistive forces. Okay, or sometimes we call it drag force. So I will mix the two words together since we are not spending too much time worrying about too much details. So let's talk about resistive forces. Okay, so what is a resistive force? Sometimes we call it drag force. Okay, so it is a type. It is something like a friction. Okay, so it is similar to friction in a way, in a sense that both all these forces are dissipating energy from your system. Okay, but for me, I call friction specifically for when it happens against a solid surface. So when it's with a solid surface, it's a static or kinetic friction. But if it's going through a fluid means either liquid or gas. So if it's either liquid or gas, then you get this resistive drag force. Okay, or sometimes you call it air resistance or water resistance and things like that. So it is a type of friction, but not really a friction. It's this force when the object moves through fluid. Okay, what does fluid means in physics, right? Fluid means liquid or gas. Anything that is non-solid. Okay, so anything is non-solid, because fluid you can pass, you can go inside it. So you can go into water, you can go through the air. So that's what it means by fluid. Okay, so resistive force happens when we go through fluid. So in the lecture notes, I have here like situations where we have resistive force. So a ship or a submarine going through water. So going through water is going to exert some opposing force onto it. Okay, air resistance as well. So air resistance in skydiving or when you're driving, in fact, sometimes it's a factor for cyclists. If you want to race, you need to worry about air friction. Air friction will oppose your speed, so that will cause you opposing force. So these two are examples of resistive or drag forces. Okay. New question, is it? Does it become kinetic friction? Yes, it does. Yeah, definitely. Yeah, Jia Cheng already said yes. Because relative motion. Okay. So now, talking about this, right? So this is a new. I'm again introducing a new type of force. So we need to learn how to determine its direction and magnitude, because force is a vector as always. So the direction is very easy here as well. Direction is opposite the direction of motion. In other words, if it's moving at some velocity v, then it is going opposite. Whatever vector it is opposite of this vector. Okay, so that will tell you the direction. How about magnitude? Again, right, because this is still, for this course, we are not focusing on too much on fluid mechanics. So fluid mechanics is like one big topic. So for our purposes, it's enough to give you two situations. The magnitude is either some constant times the speed, or sometimes it's the speed square. Okay, so it depends on the situation. Okay, so it depends on the situation. And so for this case, it depends on, I think for both this case is the v square. Okay, and in the lecture notes, you can see that for usually, it's not always true, but usually for small objects moving at low speeds, it depends on v. For large object, for high speed, so if it's a very huge non-aerodynamic system, then it depends on v square. So naturally, student is going to ask, how am I supposed to know which formula to use for which situation? I can tell you, don't worry about it. Okay. Usually the question will tell you which formula to use. Otherwise, it's not fair for student to know, because usually physicists also don't know. Unless you learn fluid mechanics, which is a third or fourth year course, you probably, for engineers, you need to do the experiment to measure the force for different velocity. Then only you know. Okay, so usually it depends on situation. There's so many types of possible situations out there, right? So it's either this formula or this formula. Okay, so don't worry about it. As long as all what you need to know is, given a situation, you need to know how to solve the problem. Yeah, it's possible also. Actually, it's possible also. So I'm only giving two examples. Okay, so so generally is v to some power. Okay, so m. Okay, so constant v to the some power m. It's true. Yeah, it could be 1.5, 1.2, could be anything, depending on the situation. Okay. So yeah, as long as it's velocity dependent. Any other question? So if not, right? If not, let us see what happens if we got this situation. Okay. So let's try to solve this. So this is in example 4.4.2.2.6. Okay. So in this example, we are just talking about a ball falling through air resistance. So the formula, you see, the question will just tell you which formula to use. And then k is a positive constant. Okay, so what is the velocity of v as a function of time? So that is the thing that you need to worry about, because that will involve more calculations. So yeah, so let's try to see what is going on here. So this is a falling ball in gravity. So let's draw the vertical direction. So this is example of a falling ball. And let's draw the forces acting on this. So it is falling because there's a force of gravity that is pulling it down, and there's air resistance. So there's air resistance, there's an opposing force, so the direction is opposite to the direction of motion. So this thing is definitely falling down, right? So it's falling down, therefore my friction will be opposite my velocity. I got kv. Okay, so the magnitude here is given by kV. So let's try to figure out the net forces in the vertical direction. So the vertical direction or vertical components is what? So I got my net vertical force is equals to, I will take down as positive. Okay, so let's take down positive. So if I take down as positive, then my net force is mg minus kV. Okay, so the drag force will reduce the force due to gravity. It will counteract the force due to gravity. And by Newton's second law, this net force is equals to mass times acceleration. Okay, so now at this stage, how do you find the velocity as a function of time? So this is the trick, right? So remember, I want to find v. Okay, so I want to find v, and I want to see how v changes with time. So how to do that? So to do that, well, we just need to remember that acceleration is the derivative of velocity. So actually this equation can be written as dv dt. Okay, so this is a differential equation, but this is still a first order differential equation, so it should be quite easy to solve. I will show you how to solve it now. So how to solve this? Well, let me simplify this equation first. There's this m here, so let me divide both sides by m. So I got g k over m v, and then this is dv dt. Okay, and then so what I can do is I will bring the dt up and bring this v down, because this term contains v, so I can put the v together, so I can integrate it. So what I mean is I do this, and then on the other side I just got dt. Everyone follow what I'm doing so far, right? Or is this too easy? Am I going too slow or too fast? Okay, so I just got this, right? And then yeah, it's just the integration now. So all I need to do is I just need to integrate both sides of the integration. Okay, so so I can make this a definite integral. Let's say the object fall from rest, right? So at time 0, the velocity variable is 0, and then at some arbitrary time t is going to have some final v. Okay, so this will give me a function of v as a function of time. So how to integrate this function? This is 1 over a linear term. So 1 over a linear term, the antiderivative is a logarithm, right? So it is m over k logarithm. Am I right? So g actually no, I don't like logarithm when there's a dimension quantity inside. So let me take out the g. Okay, so 0 to v dv g 1 minus k over mg v. So the terms are dimensionless. It's just a personal preference. Okay, I don't like having dimensions inside logarithm and sine and cosine. So then you just integrate both sides. So if I integrate both sides, I got g minus mg over k. Hang on. So k over mg, right? Yeah, so g minus mg over k, and then ln 1 minus k v over mg. Okay, so I got this now. Oh yeah, this is 1 over g. No wonder it looks weird. Okay, so the range is from 0 to t. On the right hand side, I integrate, I just get a g. Okay, so I cancel my g here apparently, and then I just simplify, right? So if I plug in the limits, I got ln. Okay, so ln 1 minus kv over mg, and then minus ln 1, which is 0, and then I bring the term over here, I got kt over m. Okay, so ln 1 is 0. So I want to find v as a function of t, so just solve this equation for v. Right, so to solve the equation for v, I just take the exponential of both sides. So I take e to the power of both sides, just means that our exponential will cancel the ln, and then on the right hand side is just e kt over m. Okay, and then I just solve this for v. So this thing is equals to 1 minus e kt over m. Therefore my v is just mg over k, 1 minus e to the power of kt over m. Okay. So do you guys follow so far? So I think this is the first heavy calculation I'm doing in this course. So it's to solve a differential equation, right? So it's just mathematical stuff, right? So this v is a function of t. Okay, so we can actually see how this goes. At time 0, the starting time, e to the power 0 is 1. 1 minus 1, 0. 0 velocity. Okay, so I can draw the graph. So I can draw the graph over here. Okay, so let's see how the graph looks like. Okay, so how does the speed change with time? Okay, so at time 0 is just 0, and then after it's 1 minus the exponential graph. So 1 minus exponential graph is something like this. Okay, and then notice that e to the negative power, right? So this term is always smaller than 1. So it's 1 minus a number smaller than 1. So it will never go beyond a certain maximum value. Notice that it will be asymptotic basically to this line. Okay, so it will be something like this. Okay, your calculus class will teach you a better way to sketch this curve, right? So I just want to show you the shape only. So this line is mg over k. We can get this asymptotic line, asymptotic final velocity is to take the limit where t goes to infinity of my function. So it's basically taking the limit of t goes to infinity of this formula. And the answer is mg over k. So we call this the terminal velocity. Okay, any questions so far? So everyone is okay? Huh? This is the terminal velocity. Okay. So now, so this is a mathematical way to get your answer. Another way to get terminal velocity. So and this is the definition of terminal velocity. Okay. So what do I mean when I say terminal velocity? It is actually the velocity. Okay. Although what I got here is speed, but I already know the direction is going down. Okay, so just include the direction, you get the velocity. It is the velocity when the net force are 0. Okay, becomes 0. Okay, so what was my equation for net force just now? Remember, my net force was downward force minus the friction. So when it becomes 0, okay, or another way of saying is that this is the general formula for my net force. So when the object is not moving, the net force is actually mg. When the object starts moving, the net force is mg minus this number. So when I reach a maximum value, so v becomes the terminal velocity, I will reach a point where, so if I increase more and more, right, I will increase more and more until it cancel out this term exactly. So it will increase to such a value where this is equals to 0. So I got mg is equals to kv terminal. So the v terminal is just mg over k. Okay. So this is another way to get your terminal velocity. K, the friction coefficient. So for this context, for drag forces, let's not call it the coefficient of friction. It is the drag resist. Maybe it's a resistive constant depending on the textbook. But for now, I'm not giving it a name. Okay. So yeah, it is some constant related to the force, but I try not to call it friction coefficient it is because we already learned the mu s mu k. Okay, so those are different story. Okay, so that one is under the friction. Okay. Okay, so what time is it now? Okay, still got time. Let's quickly do the next example, which is about skydiving. This is the terminal velocity for when the force is given by this formula. Okay, so what is this example? 2.2.7. So this is example 2.2.7. Okay, so I want to find this example is about finding the terminal velocity for this case dv square. Okay, so same thing, we are still talking about a skydiver. So okay, skydiver is a person, okay, falling out of a plane. Before opening the parachute, he is undergoing free fall. So free fall means there's no external force, so there's just mg, but he is falling through air. So if it's falling through air, there's going to be the resistive air resistance. So my net force acting on this person is mg minus dv square. So I want to find the terminal velocity. So same story as before. If a v is a very, very small number, then my net force is not 0. So if I keep on increasing, right, eventually I increase to a point where my net force becomes 0. So once my net force becomes 0, I reach the terminal velocity, and F net is equal to 0. So this is the velocity where V terminal is just mg over d square root. Okay, so I forgot to explain what is the significance of this. When V, right, is either this equation or this equation, when V increase until it cancel out to become 0 net force, what does it mean by 0 net force? 0 net force by Newton's law means 0 acceleration. So once you reach that velocity, the acceleration reduced to 0. Once you get 0 acceleration means no more changing velocity, right? 0 acceleration. So your speed is constant. So once you reach that speed, it will become constant. Okay, so it's asymptotic lah, but it's approximately more or less constant. Okay, so over here your speed start from 0. So this is referring to this case. So speed start from 0, it will go faster and faster, but it can never go faster than this speed. So this is the terminal, that's why I call it the terminal velocity. Yes. So yes, I'm skipping the details. So for this for air resistance, right? For air resistance, okay, so I was saying it, the constant is either constant V or constant V square. In fact, for both of this situation, what is the value of the constant? It depends on the area of your body, right? So because the air resistance is the interaction with the surface, so you have more surface, right? Yeah, I should add this for your knowledge, even though we are not really worrying about it here. So the constant may depend on possible factors. Number one, surface area of the body. Okay, so because when you have more area, you have more interaction with air molecules, and more interaction with air molecules, more resistive force. So it depends on surface area. So that's why your aerodynamic shape is important when you design aeroplane or cars. Okay, and then it depends on the type of fluid. In fluid dynamics, we call it viscosity, and then material of the object. What else does it depend? Those are the main things. And then depending on further situations as well. Yeah, so it's how the area is distributed. With hole is always less air resistance. Yeah. What do you mean by a plane with hole? So yeah, so what you are saying is like all these aerodynamic, fluid dynamic things are like this. Okay, let me draw a bullet. why a bullet is having this shape, okay, and then there's a sharp corner at the back, but in the front is smooth because the air will flow like this, so it has less resistance. Okay, so imagine a square thing. Okay, so it will be it will flow through very big, so this one has more drag or more resistance, this has less drag. Yeah, so if you're talking about with holes, right, is there an airplane with holes? Yeah, so I can't think of anything with hole. With hole. Never mind. Maybe you can show me a picture later. But if you take a square, right, and then if I move this square here, it will have a lot of drag. But if I cut a hole, I guess that's what you mean. If I cut a hole here, the air can pass through, so it's less air resistance. Yes, parachute. Yeah, okay, yes, parachute is a good example. So parachute, right, so if you have like this, so the purpose of parachute is to slow down your fall so that you don't fall too quickly, you smash to the ground and you die, right? So so parachute, you got this, and then if your parachute have a torn hole there, less air resistance, so you still fall down very fast, and that kind of situation. But of course, like more advanced design parachute will have some slits here so that you can control the airflow, you can control your direction and all those kinds of things lah. So yeah. So yeah, so that is air resistance. Okay, so maybe I can Google something. Let's say car aerodynamic fluid flow. Let's look at pictures. Let's see what pictures that we get. Okay. Yeah, so that's why the shape and the area of the object is important, because you want to have a smooth flow. If you have a smooth flow, less turbulence and less things like that, and then you have less air resistance. Okay, so we got about 6 minutes left before we can take a break. I should start talking about centripetal force, and then we break, and then we do tutorial. Okay, centripetal force is one last thing to talk about in this chapter. So let's talk about the centripetal force. Am I still recording? Test, yes, recording. Okay, so before we break, let me at least start this part, 2.3, centripetal forces. Okay, so this is the force related to circular motion. Remember in chapter 1, circular motion, okay, we calculate the radial acceleration, or we call it the centripetal acceleration. Right, we found the magnitude of this is just the speed square divided by r. Okay, so we were talking about a circular motion, so the object is moving in a circle, right? And let's say my object happens to be here, and I have shown you twice, one in the lecture, one in the tutorial, that the direction of acceleration is towards the center of the circle. Okay, so now remember, acceleration is a vector. So let me show you how to write this in vector form. Okay, so a vector must involve a magnitude and direction. So the magnitude is v squared over the radius of the circle. Okay, so let's say the radius is r, and then the direction is the unit vector for the radius. Okay, so this is a unit vector that is in the radial direction, and then negative, so it's pointing this one. So r is the radial unit vector. Okay, so so this is how you write this in the in vector form. Okay, and then this part is the magnitude, which we already have been using. Okay, so this one is, I'm just reminding you what we did in what we did in chapter 1. But we have learned chapter 2 also, right? In chapter 2, the main thing that we learned is Newton's law. So Newton's law, F equals to ma. That means acceleration must be caused by some force. So now we want to talk about this force that causes a circular motion. So let me say that by Newton's second law, acceleration is caused by some net force. Okay, so the net force related to centripetal acceleration is the centripetal force. Okay, so that is the concept of the centripetal force. Okay, so what time it is? What time is it? Okay, so still got some time left, so I should add some remarks. This centripetal force, right, is, well, important thing I want to mention. I have over this chapter 2, I have been introducing new types of forces, and then every time we talk about new type of force, I teach you how to get the magnitude, how to get the direction. This centripetal force is not a new type of force. Okay, means that it is just a combination of forces that we already know. Previously. So it depends on the question. Okay, so sometimes if this object is attached to a string going in circular motion, so it's going to probably be a tension. If it's attached to a spring, maybe it is Hooke's law. Okay, maybe it is moving against a surface, so maybe it is a normal force, right? So it could be any one of those. So this is what I mean by not a new type of force. Okay, so it's just a combination of forces that we already learned. So so in order to determine this, to solve this centripetal force, like to solve this type of circular motion problems, we draw the free body diagram. Then the net force component in the radial direction shall be the centripetal force. Okay, so this is what I mean. Does anyone have any question? Okay, so if there's no question, let's take a, yeah, so we are a bit rushing of time, right? So let's take a 5-minute break about there, and then when we come back, we will do tutorial questions. Okay. Testing. Okay. I think I should speak louder. Okay, yes, okay, good. So let's continue. We continue with tutorial. Okay, so let's look at tutorial 1. There's 2 more questions, so I think I'll do one of them, which involves relative motion. The second one, the method is the same, so shouldn't be too difficult. And after this class, I will upload the solution for tutorial 1. Okay, so yeah, I'll do that. If I forget, remind me. But yeah, I'll upload all the answers after tutorial 1, so because I didn't solve all the questions here, right? So let's look at question 13. So let me show this on the screen. Still recording? Yes, good. So question 13 is about relative motion. A small boat is headed to a harbor 32 kilometers northwest of its current position, and then engulfed in fog, blah blah blah, whatever. The main point is here, compass bearing of northwest and a speed of 10 kilometers per hour. So this information is telling you the velocity relative to water. Okay, so this sentence here. Then after this, what it say? It says that 3 hours later, the captain realized he's exactly 4 kilometers south of the harbor. So yeah, take the usual vector components. We want to find the velocity of the water current. So let's try to solve this problem. So let me go to full screen like that. Oh yeah, let me take it away, take this thing down, and full screen. So we are doing tutorial 1, question 13. Okay, so what is the situation? Let's say my harbor is here. Okay, so harbor, doesn't matter what this thing is, it's just some point that we're interested in, right? So initially, right, the harbor is north east or northwest. It should be northwest, right? So it should be northwest of its current position. So northwest means, is it too bright? Hang on. Okay, so northwest means, okay, so this is a 45-degree line. This is purely north. My ship is initially here. Okay, so north, south, east, west. Okay, so my ship is initially here. This is 45. And initially, this is 32 kilometers away. Okay, so this is the initial setup. And then 4 hours later, so 4 hours later, the ship is 4 kilometers directly south. So this distance is 4 kilometers over here. Okay, so from here to here, this is a vector xy axis, so we can calculate its displacement. I will show you how to calculate this later. It should be quite easy, but for now, remember that this is a relative velocity question, so I need to decide who is A, B, and P. Okay, so the P is my main, usually is my main object, so let's take the boat to be P, and then A is the earth or the ground or the harbor. Okay, so this is a fixed coordinate system, and B is a moving system, so it is another system, it is water. Okay, so from here we use our relative velocity equation. The velocity of P as observed in the A coordinate system is V as relative to the water plus V water relative to the ground. So the question is asking you what is the water current velocity, which implies that it is the velocity of water relative to the earth. Okay, so this is what we want to calculate. So this is the velocity of water current. So how do we solve this? Now, firstly, I will say this later. So let's talk about this first. Okay, so what is the velocity of the boat relative to the ground or the earth? Right, so the earth is this. Initially the boat is here, 3 hours later the boat is here. So if I can get the displacement divided by the time, I will get this expression. So how to get this? So based on this information, it says that after 3 hours the boat is here. So the boat is here, that means the displacement relative to earth is this formula, which is the displacement of the earth relative to the earth is, how to get displacement? It's a vector, right? You need the x and y components. So what is the x component? Well, this boat has moved to the left by, how far is this? This is 32, this is 45, therefore this is 32 cos 45, right? So I got the horizontal displacement. I moved to the left, therefore I got negative 32 cos 45 in the I component. How about the vertical? So the vertical is, I move up, but up by how much? Well, this is 4, so this should be 32 sine 45, which is the same as cos 45, but you minus 4. Agree? Okay, so hopefully everyone is agreeing with this. If not, you can ask me to elaborate. Sine 45 minus 4 kilometers. Okay, this is in the j direction. So therefore the velocity is v pa. So we are talking about relative motion. So most of the relative motion question is having constant velocity. So we just take the total displacement divided by the time, which is 3 hours. So in other words, we got well, let's just write this 32 cos 45 over 3 hours, and this is 32 sine 45 minus 4 over 3 hours j. Okay, so if I work out the numbers correctly, I should get 7.542 I, and this number is 6.029 j. Okay, so I got VPA now. So I got this term now. Okay, so if I can get this, I can solve this equation. So the next thing is to get this VPB. So how to get VPB? So according to the question, captain maintains in the compass northwest direction, and then is moving at 10 kilometers per hour, right? So I can get the velocity vector Vp relative to the water, because when you control the boat, remember I was saying when you control the boat, usually you can control it relative to the water because your pedal and rudder is interacting with the water. So that's why you control the velocity relative to the water. So 10 kilometers per hour, that's the magnitude. Northwest is going to be left by 10 cos 45. Okay, moving to the left, so I got minus. And then up north, so is 10 sine 45 j. Okay, so sine of 45 degrees is 1 over root 2, so it's basically just 10 over root 2 I plus 10 over root 2 j. And numbers wise is minus 7.071 I plus 7.071 j. Whichever way is up to you to keep it, right? But anyway, we got the expression already. So I want to find this equation. So therefore, VBA is equals to VPA minus, right? So I bring this over to the left hand side, minus VPB. Okay, so I got these two already just now, right? So VPB is here, and VPA was this thing. So now we have everything that we need. 7.542 I plus 6.209 j minus negative 7.071 I plus 7.071 j. So if you get the numbers correctly, I got negative 0.453 I minus 0.862 j. So this is measured in kilometers per hour. Okay, follow so far? No question, huh? So this is for page 6. Okay, so I'm recording. Yes, everything is passed. Yeah, so no other question. So you can try to do this yourself. Later I will upload and check your answer. So tutorial 2 is the one with the, oh, this one is the one with answer. So let me show you the one without answers. Yeah, you should try it first now. Okay, so let's see tutorial 2. So let's warm up with question 1, which is the easy question. Upload by Moodle. So Zuri, for the quiz, right? Quiz you upload by Moodle. So in the Moodle web page, student view. Hang on. So this is the view as I am the host of this. So let me, just to show you how it looks like, right? I forgot how to do this. Edit settings. And let me make it visible now. So let me make it available since yesterday. So definitely student can see this now. So save and return. It should refresh. Wait. Hang on. So let me, I will show you how. Edit settings. Okay, what if I delete this? Okay, so if I delete this, and then you can see this now. So so let's say I'm a student, right? So this is what you will see. Okay, so this is what you will see. So the trial quiz here, right? So you can download the quiz question here. The trial quiz is just stupid questions, okay? So don't worry about it. And then what you can do is you can submit by pressing this button. Okay, so pressing this button, and then you can upload. Okay, so from here you can, once you have solved the quiz, right? You have scanned your PDF document or whatever, you got a PDF file. You just you just browse and you upload. Choose the file to upload to here. Okay, so remember to press save changes. The button to submit is here. Can you see? Okay, so you submit through here. Submit your quiz through here. Okay, but don't worry lah. If you have problem, if you still have problem, you can, but convert to PDF because because if it's not PDF, it cannot submit. Okay, so just PDF, and there's many ways to after you take the picture, you change the file to PDF. I was just saying just now, after this class I will upload tutorial 1 to Moodle. So don't worry, I will upload tutorial 1 to Moodle. For tutorial 2, I'm just gonna randomly choose some questions lah. But okay, so I plan, right, these 2 questions I think is the hardest one. I will do it next week. Okay, I will do it next week. I will do maybe some of the questions here. Okay, if you have got any requests, you can let me know. So which one should I do? So all these are considered easy questions, right? And I don't know how much time I have left. So let us start by doing 7 and 8. These are the main concepts that I want to get across. So let's do question 7 first, and then 8. Okay, and then anything else, and then I will randomly choose some questions before if we have any more time. So let's do 7 and 8 first. Okay, so let's start doing. Open a new page. So page 7. Let's do tutorial 2, question 7. Okay, so tutorial 2, question 7. We are going to full screen. The question is: Kathy and Tommy stand on a platform of negligible weight, and then in this situation below, so Tommy weighs 500 and Kathy is 400. So she is holding the system together, so that is why the platform doesn't collapse. What downward force is she exerting on the platform? So let's try to solve this problem. So Kathy and Tommy, right? So the picture looks like this. We have let's draw platform. Tommy is standing here, Kathy is standing here. She is holding a system. So this system is hanging from a ceiling. Okay, and then I have a rope here like this, and then like this. Okay, so these are fixed against the wall. So and then this pulley is fixed position, and this pulley is supporting the platform here as well. Okay, so I have 2 strings in this question. So I have 2 different tensions. So this is one string all the way here. Okay, remember what we discussed last time? It's an ideal non-stretchable string, so it should have one tension T along the whole way. So if it's this part is T, this is T, is still T all the way. Okay, now here's the thing. What is the tension of this other rope? So let me tell you that it is 2T. Do you agree? Okay, the reason why is because let's look at the force on the pulley. Okay, so I'm drawing this pulley here. Okay, so this pulley here, there's a string coming through here and coming out again here, and then it is tied at the center towards the platform, right? So the tension on this pulley is these two are the same string, so these two each contributes a tension T going up, and then this pulley should be in equilibrium. This whole system is in equilibrium, so in order to balance this force, T2 must be equals to 2T. So that means this thing is equals to 2T. Do you agree? Okay, so I got 2T over here, and then let's try to figure out the forces acting on other parts of the system. So let's look at the force acting on the platform. Okay, so for the force acting on the platform, let's draw what is happening to the platform. Okay, so what's happening to the platform is I have Tommy standing on this part. Tommy's weight is 500 newtons, so for the case of Tommy, the normal force is equals to his weight. So Tommy is exerting a downward force of normal force 500 newton here. Do you follow? Right? And Kathy is standing here. So Kathy is here, and Kathy is exerting some unknown normal force. It will not be equals to her weight. We'll see why later. For Tommy, yes. For Kathy, no. This part is attached to the 2T tension, so I got 2T. Okay, so then platform is also in equilibrium, so therefore the net force acting on the system is, let's take up as positive, so I got 2T minus 500 minus this unknown force should add up to 0, so I got this equation. So 2T is 500 plus n. Okay, so apparently by drawing free body diagram, I got these two unknowns, so I need a second equation to solve. So I just need another equation to get n. Right, so to get n, well, let us draw the force acting on Kathy. So what are the forces acting on Kathy? Okay, so Kathy is holding on to a string, so therefore it is the tension T, right? Just one T. She's holding one piece of string here, and then she is having a weight, so we got mg, and Kathy's weight is 400 newton. And then she's standing on the platform, so the platform exerting the normal force. So you see, these two forces are equal and opposite, right? So these two forces are equal and opposite. This is because of Newton's third law. Okay, so one is down, one is up, equal and opposite forces. Okay, so Kathy is in equilibrium, therefore still taking upwards as positive. So the net force acting on Kathy is T plus n minus 400 is equal to 0. So I got T is equals to 400 minus n. So I got a second equation, two equations with two unknowns, so enough for me to solve. I will substitute equation 2 into 1. Right, so on this side, 1 becomes 2. 400 minus n is equals to 500 plus n. Okay, so I can solve this equation now. So 800 minus 2n is equals to 500 plus n, so therefore 3n is equals to 300 newton, so n is just 100 newton. So the normal force is 100 newton. So Kathy exert on the platform is 100 newton down onto the platform. And no question? Everyone clear? Okay, so that is how we get the force of Kathy. What's my time? So can we calculate the pull by treating everyone on the platform as a whole? We can. I have not tried it, but can you get the answer? You can treat it as a whole, but if you treat everything as a whole, right, the normal force is an internal force. So the whole will not tell you information about internal forces. You can try it, right? Then you see that there's no n anywhere. Is that your question? I assume that's your question, right? Yeah. So you can treat this whole thing as a whole, then you just get the total weight of the system supported by this T coming up, right? So this T go up and down, cancel each other, and then this one is internal to different parts of the system. So you just get the whole system with this T. You can get T from there, right? So once you got T, then you draw a Cathy free body diagram. Yes, then this way you can. Maybe you can. Yes. Yeah. We are yes, T is the force Cathy exerts on the rope, but we are just calling it T because she's holding on to the rope, and then the rope will have the tension T. Yeah, she's holding on to the rope will have a tension T. Clear so far? Okay. I can't decide what to do next. Oh yeah, just now I was saying I'm doing question 8, right? Question 8 is a slightly tricky question. So yeah, let's do 8 next. Everyone is okay with this part already, right? So let's do the next question. So the next question is question 8. Let me show you the question. It's over here. Okay. Question 8. So it's too big. So I have a child named Pat who wants to climb a tree, right? But he wants to go up by sitting on a chair and pulling onto the system. So basically this situation here. You are given the tension on the string. So this information is telling you that the tension on the string is 250 newtons. Pat's weight is 320 and the chair is 160. Okay, so yeah, let me write down the information that is given to you. I will switch the screen later, but let me write first. This is tutorial 2 question 8. Okay, I want to know Pat's mass. That will help us make it easier to calculate, and then the chair's mass. Okay, so yeah, so just remember this picture, right? The kid is pulling onto the string such that the system is going up. So there's two pieces here, the kid and the chair. So we want to solve this system. So let's see how we figure this out. Okay, so based on the information given, we are given the weight of the kid, Pat. So from the weight, we can get the mass, which is thus 320 newtons divided by G, which is 9.8. So you get 32.653 kg, right? I don't care about significant figure because this is not my final answer. So the chair mass is 160 newton divided by 9.8. You get 16.3265 whatever kg, right? Then the first thing that we want to do is I want to draw free body diagrams for this, and also for the system as a whole. By the way, information given is tension along the string is 250 newtons. So T is 250 newtons. So let's try to draw. First, let's draw the kid's free body diagram. So only draw the forces acting onto the boy, right? So what are the forces acting onto the boy? Firstly, there's a weight, mg. So mg is already 320 newtons. This one we know. He's holding onto the string. So holding onto the string means there is a tension T. And remember, right, always remember, tension T is always away from the object. So we got T, which is 250 over here. Okay, and he's sitting onto a chair. He's interacting with the chair's surface. So the chair will exert a normal force that is going up. Okay, so when you're sitting on a chair, you will feel a normal force coming through you upwards. So I have 3 forces there. Okay, so this is the free body diagram. How about the chair? So chair free body diagram. So we only look at what is acting on the chair only. Okay, so the chair is attached to the string here, right? So I got the tension T, which is 250. The chair's weight is 160 Newton. And then the boy is sitting on the chair. So the boy is sitting on the chair means the boy is exerting a downward normal force acting onto the chair. So this is the Newton's third law. Okay, so this is because of third law. Equal magnitude N, but opposite in direction. This is third law. Okay, but anyway, we don't know what is N yet, but these are the free body diagrams. Then we should also draw the free body diagram of the total system. So the boy sitting on the chair, now we take the whole system. Okay, so for the whole system, the chair has a string attached to it. The boy itself is holding onto the string. So there's a tension T, there's a tension T here. So both are 250, right? And then there's a pulley that will loop it around. But we only look at the forces. So there's two forces acting up. And then the chair's weight is 160 Newton. The boy's weight is 320 Newton. So this is the free body diagram of the total system. Understand so far? So, understand? I want to show that the system is accelerating upwards. Okay, so how can we prove that the system is accelerating upwards? Well, let's just look at this system, right? So this is already inbuilt there. Let's look at the total system. Okay, so from here, the system as a whole, total mass is the mass of the combined system. So everything, that means the mass of the boy plus the mass of the chair. Okay, so this is the total mass of the system, is this number plus this number. I did not calculate this number, but it's just these two numbers. Anyway, we don't need. But what is the net force? Okay, so the net force is, well, we take upwards as positive. So the net force is T and T, so I got 2T, and then minus 160 minus 320. Okay, so this number is 250 newtons each, minus 160 minus 320. So this is a positive number, right? I did not calculate this, so let me do it now. Okay, so this force is 250 minus 160 minus 320. So this net force is 20 newtons. Is positive. It is a positive number. Positive number, that means there's a net force going up. So the system is moving up. So there's a net force, hence net upwards acceleration. Okay, but we should also calculate its magnitude. So to get the magnitude, we use second law. So by Newton's second law, the net force should be equals to the total mass of the system times the acceleration. Right, we got the net force is 20 newtons. The total mass is so it's 32.653 plus 16.3265, so it's 48.9795 acceleration. So the acceleration is 20 divided by this number. I got 0.408 if I keep it up to 3 significant figures. Okay, so the magnitude of the acceleration is this. So the system is accelerating up at this acceleration. Follow so far? So everyone understand the question? Okay. The final part is to find the force that Pat exerts on the chair. So just need to find the, okay, thanks. Just need to find the normal force, the N. So now we want to determine N. So at this stage, N is unknown. You mean the Pat question? This question? So this question. So It's because it's one string. Okay, so let's the chair there. Yeah, because I have a chair and then the boy, right? I have this picture. So he's holding on the string on one side, and then let me use red to draw the string. Okay, so what are you? Oh, Kaheng, you understand now? Just to make sure, right? So the system is like this, right? The system is like this. For tension, right, you just need to look at the tension at every part. So this part is attached to a string, so tension has a force that is always going away. Fine. Then this part is attached to a string, so there's still another tension also going up. And then the magnitude. So the magnitude of this tension is T. And then this is the same rope, so it is still T for both. So that's why you have two tensions going up. Okay, so let's say the boy let go of the string. So if the boy let go of the string, that means there's only one tension left on this side. But if you let go of the string, the system will fall. But instantaneously after you let go, only one tension left. That's why the net force it will fall down. Okay, understand everyone? The whole. Okay, so if you have any question, you can type it in. I will. Okay, good. Thanks. I will continue C. So C is just to find the normal force. No space. So let me go to the next page. Part C is to get the normal force. So for the normal force, finding N. The force that the pad exerts on the chair. So the force that pad exerts on the chair. So let's look at the pad free body diagram, right? So use pad free body diagram. So we have drawn this free body diagram already. So let's take upwards as positive. So the net force is N plus T minus the weight is accelerating. We have also calculated the acceleration. So mass times acceleration is over here. So we have all the terms already because I know T is given to be 250. The weight of pad is 320. And then the mass of pad is 32.653 kg, and then we computed the acceleration is 0.408. Okay, so so let's see if I can get this correctly. 32.653 times 0.408. Okay, so I got this number on the right hand side, and then plus 320 minus 250. So it is 83.3. So N is equal to 83.3 newtons. Okay. Wait, I'm recording, right? Test. Yes. Still recording here. Yes. Okay. So so the answer is just the normal force is 83.3, and then the direction I've already said here is the pad exerts on the chair is down. Right, so pad is what the chair is experiencing, the downward force of 83.3 Newton. Equal and opposite reaction. Okay, so clear so far? Okay, so let's do another question. I think I want to do the elevator question. Okay, so that's question 4. So, tutorial 2, question 4. Because this is also another thing I want to talk about. Okay, so let's do question 4. So, what's question 4? Yeah, let's show you question 4. So, question 4 is this. Zoom out a bit. So you go into an elevator, right, and you step into a scale and then you push the up button. So this is just to say that the acceleration is going up. Your normal weight is 625 newtons. from this information also you can calculate your mass if you want. And then if the elevator is accelerating as this much, how much does the scale read? And then blah blah blah. So this part, once we solve part A, should be easy to get part B later. So let's try to figure this out. Okay, so this one, take it out, full screen. So what is this question about? So this one is implicit, which I haven't mentioned yet. So let me talk about this now. The main point that I want to show you guys is that when we use weighing scale, right? Okay, weighing scale is to measure your how many kilograms you are. But what is actually measuring is to measure your weight, right? And then they divide by G to get your mass. Then you tell you your kilogram. But how do they measure it? So you step on the weighing scale will measure something. And what is actually measuring is the normal force. Okay, weighing scale measures normal force. Okay, why? Because if you stand on the weighing scale, okay, you can only measure the interaction that is coming from you. So by Newton's law, so if we measure N and then you have a weight, as long as you are in equilibrium, okay, then the normal force will cancel with the weight. Therefore, the normal force will give you equals to mg. And then this part is measured by the scale, okay, and according to the question it is 625. So you can get your mass in kilograms by 625 and then divided by G. So 625 divided by 9.8 is 63.776. So 63.776 kg. So that's how you get your mass in kg, right? So that's all the steps that is hidden from you. So now you know, right? So the main point is wow, very advanced. Carbon 12. What kind of scales with carbon 12? Atomic weights, atomic mass unit, right? So oh yeah, what I was saying is you need to make sure that you are not cheating to get the correct scale, right? Because when you stand on the scale, if you support yourself onto something, then you see your reading of the scale will be lighter, correct? Why? Because if you are cheating by weighing yourself, right? Let's say you're holding onto something, right? You're holding onto something with a tension T, right? You're hanging onto something, and then you have your normal force and then your mg, then your net force becomes this. Okay, as long as, but if you're still not accelerating, then your weight will get a smaller number. Okay, so then that's how your weighing scale can change. If you support yourself onto something else, right, then you get the n that is different, and because your n is different, your weight is wrong. Okay, so that's why you must let go and don't touch anything to get your correct mass. That is what it means. So this is just talking about weighing scale. But for question 4, right, we are talking about the weighing scale inside an elevator. So what happens inside an elevator? This is kind of like Einstein's equivalent principle, but a very, very simple case, right? So you are standing on the weighing scale inside an elevator. What are the forces that is acting towards you? So according to the question, your elevator is going up, A, right? And then what are the forces? So you are standing onto something, so you are touching the surface, there's a normal force, and then you have a weight, mg. But your system is accelerating. So what is the net force acting on you? We are looking at the vertical components only. So the net force is m minus mg. But by Newton's second law, net force is also equal to mass times acceleration, which is not 0. So if it's not 0, then I got this term, equation here, right? So if the elevator is not accelerating, then your weighing scale will give you your weight. But if the elevator is accelerating up, your weighing scale will go higher. Okay, so it will go higher, and it will be higher by how much? So by this much, and your mass was 63 kg, right? And then it's 9.8 plus the acceleration is 2.5. So if you compute everything, you get 784 newtons. Okay, so it is not the same as your original mass 625. You can actually try this if you stay at a place with an elevator, right? Or if you're allowed to go to the A1 to A4, A5 lift, right? And if you bring your elevator scale, your weighing machine, and then you go inside the elevator and you stand on it, and then you go up, and then you come down. Let's see what you get. Okay, so can I make this a assignment? It's probably not enough, but it is a fun thing. So if you have a weighing scale, you can try to measure your acceleration of the lift in your building or the A2 building. Okay, so you can measure the acceleration, and then if so this is maybe the more I think about it, the more fun. Okay, you want to go later. So Wei Zheng got a weighing scale, and the canteen elevator. Yeah, you can try that. Okay, so you can tell us the answer when you get back. You look at a scale, right? And then based on this equation, we should be able to calculate the acceleration of the elevator. So you look at what is the highest number it will give you. Okay, minus mg. Okay, so this, remember the weighing scale, it will give you in kg only, right? So it will give you in kg. So to compute kg, it will be effective mass times g, n, right? So it's equals to n. Okay, so basically, yeah, so it will give you this reading. You need to times g to get the highest n, and then you divide by your own mass. So from here you can calculate the acceleration of the elevator, right? So if you get this information already, right, you can probably get some other information. If you want to yeah, that's disappointing. Yeah, because we can calculate the acceleration of the elevator, and the elevator can also, it will tell you the maximum passengers, and sometimes it will tell you how many kg it can support. Some elevators will put a sign there. Then so this is the maximum passengers, and then maybe you can estimate like what is the mass of the box itself. So you can also calculate what is the tension along the cables, right? And then you can calculate why do we have a maximum passenger, because the tension will it can only support maximum tension. If the tension along a string is too strong, the string will actually break. So that is one of the issue that we want to worry about. What do you mean? Oh, I mean, I'm chit-chatting along with you guys also. So, yeah, the m mass on the scale. Yes, correct. So m, because the reading on the scale is giving you in kg, so it should be this number in kg. So you need to times g to get the newtons. So that's what I meant. Yeah. Okay, I get it now. The am I a joke meme? Yeah, I remember that meme now. So any other question? Yeah, who has a weighing machine? You can try to measure this and tell me. Okay. So I'm wondering lah. Okay. If you tell me the answer, you can do one less question on the quiz. Of course, I'm a man of culture. Yeah. So fake mass, yes. The fake mass, the m is what I mean is this is the reading. The scale display. the scale will give you this number. It will give you this number in don't know how many kg lah, right? So it will give you in kg units. You need to convert to newtons. Electric scale, yes, is the same. Maybe electric scale you can change the setting, right? And then it will show you in newtons. So straight away you can do it. Yeah. Yeah, so it's something that, yeah, I think it's worth trying, at least to experience this. Yeah, tri-beam balance may not work on the elevator because it may not, maybe it will work, I don't know, but yeah, tri-beam balance is rare, right? What you have is the bathroom weighing scale, so that one should be more common than probably what you have at home. Okay, it's already 4:55. So anyone has any other question? The scale with tri-beam, the one with comparing mass, yes. Concerning the assignment, can you start doing? Yes, you can start doing if you know what to do. So yeah, I'm curious, do you know what topic you want to do already? Kaishen, which topic you want to do? Attack on Titan. Okay, so yeah, so if you want to do Attack on Titan, yes, you can do it, but make sure you answer all the physics question. Are we able to do the topic now? Well, you can start now, but some of the topics involve chapter that you have not learned yet. But maybe you already know the chapter, so if you want, you can start doing lah. The deadline is very, very late, so if you want to do it early, it's fine. Where is it? So like the space elevator involves gravity, so I haven't taught you gravity yet, but if you already know how to do it, and if you want to do it, then sure. Yeah, someone said about Edward machine, so you can. Why do you talk about everything? Oh, about the pulley question. Yeah. Propose your own problem. Yeah, Attack on Titan. Yeah, maybe you should learn deeper. So then you can start later. Yes, Roger likes it much. Yeah, so you can wait to learn the chapter a bit more first. Because the due date is the last day of semester. You can start doing now if you are free. Like you do a bit first. And then when we go to the gravity chapter, for example, then you learn something new, you can add on to it. Then that's fine. So yeah, so no problem there. Okay. So anyone else have any other question? Total force on egg fried rice. Well, if you can. I mean, if you want to think. So the Roger video, right? I don't know if you guys watch. Later, the Uncle Roger and the Hersha, they make a video together, and then where she actually cooked the rice the correct way in front of him. And then I remember the scene where she actually flipped the rice too hard and she dropped the rice there. So I don't know if there's enough physics there for you to solve it, but but yeah, there is a total force on egg fried rice. But speaking of egg, right? Do you know how to determine whether an egg is boiled or not? Is it a fresh egg or a boiled egg using the angular momentum? I'm sure some of you have heard of it. Yeah, but it's a simple situation. It's not enough for assignment. But I'm just mentioning it to you because it involves angular momentum. Oh, this is, yeah. So the chat comes up on my phone faster than on my computer. So flipping the egg, spin the egg, yes. One try only. Oh, Minkai asking about quiz. Is it one try only? Yes. Well, I mean, it has 24-hour period. You can upload, and then as long as if you can re-upload, as long as it's before the deadline. So yeah, as long as it's before the deadline, you can upload or you can delete and upload again. What else? Can you do your topic now? Yes, new messages. Yes, Zuri said about the egg, right? Yeah, you spin it and then the centripetal acceleration will be different. And then yeah, someone got a video already. Okay. Well, it's 5 o'clock already. So if there's no other question, I think that's all for today. I will do the other tutorial questions next Wednesday. So the quiz, right? The deadline even though it has a deadline, but it's not counted. But just to show you the system, I think the system will remind you of the deadline. So if you are not familiar with this system, you can log in and see where you can view the deadline. So you can see how much time remaining, okay, and then the due date is displayed here. That is the reason why I have the trial quiz, so that you can see how it works. So when the real quiz comes, you know what to do. Okay. So if there's no other question, I can stop recording. Stop recording here, and I will stop the recording on the OBS as well. So I will stop the recording here.